observation will be successful.
So that means for the next 3 months, you are going to be very busy as a team member. At Sagamihara and station and center, you're going to get involved? Yes. Here at Sagamihara, the data is going to be analyzed. So I'm going to move around different places. And at the previous media coverage, the live coverage that you came over to our place, and thank you very much. I hope that we would like to move on to the next stage of this mission. This is about XRISM project. We still have more to talk about, but later on we are going to come back to this topic. But we have to switch the camera to Tanegashima Space Center.
It will be, we have some more time. We have received more questions about XRISM. We would like to address these questions. One of the questions is, this is a report of the status of launch preparation from Takesaki Launch Control Center at JAXA Tanegashima Space Center.
H-IIA ロケット47号機打ち上げ最終実施判断の結果は GO です。
We have just given the final go decision for the launch of the H-IIA launch vehicle number 47.
現在各系統もロケット打ち上げの最終作業を実施中です。また警戒区域の安全が確認されており、気象条件も打ち上げに支障のないことが確認されました。
All systems are now in final operations. The restricted area has been vacated, and the weather is confirmed to be sufficient for the launch.
従いまして、X 線分光撮像衛星XRISM、小型付き着陸実証機SLIMを搭載した H-IIA ロケット47号機の打ち上げを本日日本時間の午前8時42分11秒に実施します。
Consequently, we proceed with the countdown to the launch of the H-IIA launch vehicle number 47 with on board XRISM and SLIM, and the launch time is set to be 8:42 and 11 seconds a.m. Japan Standard Time.
機体は最終的な確認作業が続けられており、現在のところすべて順調との報告を受けています。
Our launch site operators have given reports that the final checks are underway, and all operations have proceeded as scheduled so far.
打ち上げ8分前より打ち上げに向けた秒読みが開始されます。
We will start the terminal countdown at T-8 minutes.
480打ち上げ8分前です。現在各系ともロケット打ち上げの最終作業を行っています。 また警戒区域の安全は確認されています。
It's 8 minutes to the launch. All systems are now in final operations. The restricted area has been vacated.
460、59、58、57、56、55、54、53、52、51、450。440。430、29、28、27、26、25、24、23、22、21、420、19、18、17、16、15、
安全系準備完了。
13、
The
12、
safety system is go.
410、409、408、407、406、
車上系準備完了。
404、
The range
403、
system is
402、
go.
401、400。390。380。370。360。
打ち上げ6分前です。現在車上の天候は晴れ、気温摂氏 28.6 度、北の風
350。
毎秒 5.5 メートルです。H-IIA ロケット47号機の打ち上げに問題はありません。
It's 6 minutes to launch.
340。
The current weather at the launch site is fine. Temperature is 28.6 degrees Celsius, and wind is 5.5 meters per
330。
second from the north. The weather has no constraint for the launch.
本日の打ち上げ予定時刻は日本時間の午前8時42分11秒です。
Today's scheduled liftoff time is 8:42 and 11 seconds a.m. Japan Standard Time.
310、309、308、307、306、305、304、303、
衛星系準備完了。
301、300。
The satellite system is go.
290、89、88、87、86、85、84、83、82、81、280、79、78、77、76、75、74、73、72、71、270、69、68、
自動カウントダウンシーケンス開始。
66、
The
65、
automatic countdown
64、
sequence has been
63、
initiated.
62、
現在ロケットの管制は吉信発射管制塔から行われています。
The H-IIA launch vehicle is now operated under the command of Yoshinobu Blockhouse.
250、49、48、47、46、45、44、43、42、41、240、39、38、37、36、35、34、33、32、31、230。220。210。200。190、89、88、87、86、85、84、83、82、81、180。
打ち上げ3分前です。
It's 3 minutes to the launch.
全システムの電源が外部から内部に切り替えられました。
170
The power has been switched to the internal systems.
1段液体水素系準備完了。
The first stage liquid
160
hydrogen system has been pressurized.
150 140 39 38 37 36 35 34 33 32 31 130 29 28 27 26 25 24 23 22 21 120 19 18 17 16 15 14 13 12 11 110 109 108 107 106 105 104 103 102 101 100 99 98 97 96 95 94 93 92 91 90 89 88 87 86 85 84
2段液体酸素系液体水素系準備完了。
The second stage liquid oxygen and hydrogen system has been visualized.
74 73
1段液体水素系準備完了。
69 68 67 66 65 64 63 62
The torches are ignited.
59 58
フレーム
57
デフレクター冷却
56
開始。
55
The cooling water system for the flame
52
deflector has been activated.
50 49 48 47 46 45 44 43 42 41 40 39 38 37 36 35 34 33
ウォーターカーテン散水開始。
31
The sound suppression water system has been activated.
27 26 25 24 23 22 21 20 19 18 17 16 15 14 13 12
フライトモードオン。
10
The flight mode is on.
同様電池起動。
The thermal batteries have been activated.
全システム準備完了。
All systems are go.
メインエンジンスタート。
The main engine ignition.
SRB-A 点火。リフトオフ。
Solid boosters are ignited. Lift off.
プリズムスリムを搭載した H-IIA ロケット47号機は2023年9月7日午前8時42分11秒に種子島宇宙センターから打ち上げられました。
We have a liftoff of the H-IIA launch vehicle number 47 from JAXA Tanegashima Space Center at 8:42 and 11 seconds a.m. on September 7th Japan Standard Time.
打ち上げ以降ロケットの管制は吉信発射管制塔から竹崎総合司令塔に引き継がれています。
Following the liftoff, the operation control of the H-IIA has been switched from Yoshinobu Blockhouse to Takesaki Range Control Center.
60
打ち上げ後1分が経過しました。
It's 1 minute into the flight.
70
ロケットは現在東方向の太平洋上へ飛行しています。
The H-IIA is now flying above the Pacific Ocean to the east.
83 84 85 86 87 88 89 90
SRB-A 燃焼終了。
Solid boosters have burned out.
110
SRB-A 分離。
12
Solid boosters have been separated.
15 16 17 18 19 120 121
小笠原局でのロケット追尾が開始されました。
Ogasawara Station had started tracking the H-IIA.
第1段エンジンの燃焼は正常、制御系、飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the first stage engine, outro control, and the trajectory are all nominal. The H-IIA flight is on course.
現在のロケットの高度は約 48km、148km、秒速約 1.9km です。
Current altitude of the H-IIA is about 148 km.
上部衛星フェアリング分離。
The upper payload fairing has been jettisoned.
打ち上げ後5分が経過しました。
It's 5 minutes into the flight.
第1段エンジン燃焼停止。
The first stage engine cut off.
第1段、第2段分離。
The first and the second stages have been separated.
第2段エンジン第1回燃焼開始。
The second stage engine ignition for the first time.
打ち上げ後9分が経過しました。
It's 9 minutes into the flight.
打ち上げ後10分が経過しました。
It's 10 minutes into the flight.
第2段エンジンの燃焼は正常、制御系、飛行経路も正常。ロケットは順調に飛行を続けています。
The combustion of the second stage engine, output control, and the trajectory are all nominal. The H-IIA flight is on course.
現在のロケットの高度は約 552km、秒速約 6.0km です。
Calling output of the H-IIA is about 552 km and velocity is about 6.0 km per second.
第2段エンジン第1回燃焼停止。
The second stage engine cut off for the first time.
クリズム分離
XRISM separation.
クリズムの軌道への投入を確認しました。
XRISM has been inserted into the orbit.
ロケットはこのまま完成飛行を続け、まもなく小笠原局の受信範囲を離れます。
The H-IIA is in a coastal state now, and shortly it will proceed beyond the tracking area of Ogasawara Station.
次のイベントまで一旦実況放送を中断いたします。打ち上げから約47分後にスリム分離を予定しています。
The separation of SLIM will occur in about 47 minutes into the launch. Until the next major event, there will be an intermission.
竹崎総合司令塔からの実況放送は午前9時25分頃に再開を予定しております。
This live coverage will resume at about 9:25 a.m. Japan Standard Time.
We are watching the live coverage of the launch sequence. XRISM is separated. We have received message videos, so please take a look at them.
I'm Richard Kelly from NASA's Goddard Space Flight Center, and I am very happy that we are finally on our way into space to begin a new journey with the X-ray imaging spectroscopy mission. I want to congratulate JAXA and the rocket team at Mitsubishi Heavy Industries for getting us this far. This took an enormous amount of work, and my colleagues at NASA are extremely grateful and wish to congratulate them on their success. Astronomers from around the world have eagerly anticipated the launch of XRISM and the new capabilities it will provide for high-resolution spectroscopy and wide-field imaging. We are now a major step closer to exploring the universe in X-ray light with a powerful new tool to reveal what is going on in so many celestial objects in our galaxy and all the way out to distant clusters of galaxies that are emitting X-rays due to their extreme temperatures and energetic conditions. We will soon bring this new observatory online and get to work. So congratulations and go XRISM team.
XRISM project principal
I am Tashio, principal investigator of the XRISM project. TEMMA in the 1980s, ASCA in the 1990s, and Astro H in the 2010s. With their then state-of-the-art spectrometers, Japan always led the world in X-ray astronomy. This time again, the world's best spectrometer will be launched into the space. We are determined to use XRISM to capture the world's best spectrums to lead the world in X-ray astronomy. Please continue to support our mission.
The first video was by Dr. Richard Kelly of NASA, and the second was Professor Tashiro, principal investigator. Now we will be discussing XRISM in more detail. From XRISM project scientist, Professor Matsushita, and from Science Operation Team, Dr. Shidatsu are with us. And about XRISM science research, I would like to ask of them. First, Professor Matsushita. Yes, I was watching anxiously, but successfully XRISM was separated to my great relief. Over the next 3 months, carefully, validation systems will be deployed, and so we will have to continue to be watching carefully. But first step was successfully done. 3 months after, scientific observation will be carried out, and we would like to be able to report the first light. About XRISM satellite, I would like to explain. Can I have a slide? And Dr. Shidatsu, please explain about the XRISM and detector. I would like to explain. Can you see the slide? Is the slide being shared? XRISM length is 8 meters, about 3 stories high, and 2.3 tons is the mass, and width is 9 meters when solar panel is deployed. Height is 550 kilometers, and it's at inclination of 31 degrees, and period is 96 minutes. From the space, X-ray arrives to the left top part of the satellite and will come into the satellite. In this cylinder, there is X-ray telescope. Using X-ray telescope, X-ray will be gathered. The focus of the telescope, the right bottom area, have two detectors. First is X-ray microcalorimeter resolve. Resolve uses freezing systems, including liquid helium, and cooled to negative 273.1 degrees. And at super high resolution, X-ray will be observed. Next is X-ray CCD camera extend. In comparison to resolve, extend has wider angle and will be able to observe an area of a sky equivalent to a full moon at a time. Using these two equipments, observation will be carried out.
So, from my side, the scientific research plan of XRISM, Dr. Shidatsu will give the latter part of the explanation. Then if you go to the website, you can see how to see the cosmic winds. How should I give the explanation on this? This is the topic I would like to talk about. As has been already explained, the telescope and detectors are on board. And what is X-rays? This is the starting point. X-rays are part of the electronic magnetic waves, like the ultraviolet as well as the lights. They are part of the electromagnetic waves with the high energy, with the short waves. X-rays cannot penetrate the atmosphere, and so the satellite is essential for the observation. As has been already explained, 1 million degrees and the 100 million degrees, the objects will be able to be observed by this X-ray astronomy. There are two detectors on board. The first one is resolved. This means the resolution and also determination. So these two things are contained in this term. Now let us compare the performance. As you can see, this is about the Astro H observation results. Perceives the clusters of a galaxy, X-ray spectroscopy, and you can see the colors in the X and Y axis. You can see those are the two detectors that are going to onboard and similar to the ones that we have. The black represents the Astro H microcalorimeter, and the red one is a Suzaku CCD. The microcalorimeter, if it is going to be used, X-ray color, that is the axis, you will be able to see how accurate it is. And similar to the sound, when it comes to the light, it is affected by the Doppler effect. If it is approaching, and then the blue shift, and then if it is going distant, red shift. And this is going to be applied to the observation. X-ray color can be observed accurately, and you will be able to see the sources, or like the high temperature gas, and can be analyzed accurately. And on top of that, you can see chromium and manganese. Those rare elements, they are going to be X-rays emissions, as you can see in the chart. Those the minor the X-rays can be detected for observation. And then X-ray based space. How is it going to be observed? When it comes to the Milky Way, you can see the near-infrared observation on the top. You can see the disk that spreads around. We are within this disk. And then X-ray has observed this galaxy on the bottom. In the bottom, you can see a different view. X-rays will use emitted by the gases with high temperatures. In the case of the Milky Galaxy, you can see millions of degrees of X-rays can be observed. You can see the speed of the cosmic wind, and there are different the celestial objects. They are called supernova remnants. Those two remnants, the left one is about 300 years ago. It is the remnant of the supernova explosion, and it's 16 light years wide. And on the right-hand side, 11,000 years ago, there was the explosion. and 250 light years expanse. So you can see the effect of the explosion. XRISM will be able to observe the X-rays emitted from those supernovas, and then we will be able to observe the elements and the speed of the gases. In fact, around ourselves, when it comes into those elements, they are produced in the supernovas. And as you can see, we will be able to analyze the alchemy of the space and the speed of the wind and the evolution of the galaxies. We will be able to detect them. And you can see this round object. These are the clusters of galaxies. Hundreds of galaxies are going to be combined together. And you can see this is the enlarged picture, X-ray picture, which is enlarged, and about 600 billion years away with the expanse of several light years. And they are trapped in the high temperature gas in the core. And most of the elements in the space are produced and then exist in the form of a high temperature gas. XRISM will be able to detect these objects and then how those objects are growing in the space-time. They will be able to be observed. And there's some percentage of the elements that were produced in supernova are spreading around, and we will be able to observe them. In the core of this stellar object, this is M87. And this M87, this X-ray picture can be captured on the left-hand side. From the galaxy, there is a high temperature gas is emitting. And on the right-hand side, this is the microcalorimeter, which captures the spectra, which is expected to be captured. The pinkish, the dotted line, represents the Suzaku results. And you can see different kinds of information, the data can be captured. A XRISM satellite will be able to observe the emissions of those gases from M87. Then, how's the wind blows from this place?
Yes, thank you. Shiratsu speaking. M87 was just mentioned. In the center of the image of the galaxy, in a white square, that is the center of the galaxy. In X-ray, we can see that it is very bright. And if this is enlarged further, it is about 6.5 billion solar mass. There is a supermassive black hole. It is known to exist. And such supermassive black hole is estimated to be at the center of each galaxy. Other than supermassive black holes in the universe, there are various black holes, including small and large ones. For example, at the right side, this is a different galaxy, and visible light and X-ray are superimposed. And looking at this, other than at the center of the galaxy, there are some bright spots under X-ray. And this is also a black hole, and these are paired black holes. And these are several tens of times larger than solar mass, stellar mass black hole. And these are circling each other in a very short distance. They are attracted by the strong gravity of the black hole, and they are falling into black hole as they encircle, creating a disk at the center. And the gas temperature is as high as 10 million degrees, emitting very strong X-ray, and that X-ray is observable in the image above. There are small and large black holes. They not only absorb things, but as Professor Matsushita mentioned earlier, high-speed gas is emitted. For example, on the left side, this is a jet, and light velocity is 300,000 kilometers per second. The speed is as fast as that, and the falling disk above that, there is a wind emitted, as shown on the right side. The velocity of the wind is several hundreds of kilometers to 10,000 kilometers per second. Earlier, rocket, when XRISM was separated, it was traveling at about 8 kilometers per second. In comparison, the speed is much, much faster. And in a supermassive black hole, these jet or wind are emitted, and surrounding stars and gas may be moved and affect the formation of the galaxy itself. That is the estimate. But why do jet and wind come from the black holes? And to what extent do they affect the surrounding environment? That is not fully elucidated. With XRISM, we hope to be able to understand this mechanism. For example, as shown at left below, around the black hole, there is a wind. And let's say we observe this wind. Near the black hole, there are various types of X-rays with different levels of energy. And X-ray, the gas coming out, if we observe the wind, we can look at the element such as iron that will be absorbing a certain level of energy. And as shown on the right side, we can see a spectrum of absorbed energy. The wind is moving, and due to Doppler effect, from the original energy level, absorbed energy is observed at a little different time difference. And with that, we hope to be able to estimate the level of energy. And the black line showing absorbed energy, we were able to have very rough idea, but with the resolve on XRISM, each line of absorbed energy can be understood more precisely to understand the intensity and absorption of energy, how much gas at what velocity are emitted to the surrounding environment, and how much it is affecting the environment. We hope to understand that better. And with X-ray observation, time-space distortion may be understood. That is also hoped. Near the black hole, because of theory of relativity of Einstein, there is a distortion of time-space, and EM wave that is emitted will be observed with a distortion. The right side diagram shows the iron light line emitted from the black hole, and there are several peaks spread over widely. And this spread shows the distortion of the timeline. By understanding the shape of the emission line, we should be able to understand the degree of distortion of time-space around black hole. And black hole rotation, the faster the rotation, the effect is larger, and the range will be spread wider. So by understanding this, we should be able to measure the speed of the rotation of the black hole. Not only near the black hole, but at a distance from black hole, there may be a gas and wind that are absorbed. Then smaller emission lines and absorption lines will be mixed. With the existing equipment, it was difficult to distinguish, but with resolve, as shown in red line, various different components can be separated to understand the distortion of time-space around the black hole in more precise way. That is the hope, and in this way, so this is only a part of what we are hoping to achieve with XRISM. We would like to understand the mystery, unravel the mystery of universe using XRISM.
Thank you very much. And having listened to your presentations, XRISM has a very fancy name given to it. The resolve means the dissolution, and then resolve also means determination and fortitude, and then extend. This represents extension of the idea, so to speak. Similar to XRISM, well, as captured in XRISM, how do you come up with the specific naming? Microcalorimeter, Rich Kelly, Mr. Calorimeter, AK, who has named this machine with the instrument in that way. Thank you very much. And the viewers probably are most interested in this topic, the distortion of space-time and black holes. And it is going to go up into 10 million degrees. and I am a scientist on the solar system, and then the temperature is like 1 million degrees, but it goes up into 10 million degrees. The flare is supposed to be the reason for this kind of creation. But in terms of the theory, do you have any specific ideas when it comes to the black hole, the temperature surrounding it? The gas comes down, declines, and it resolves and rotates at a huge speed. And then, as a result, the temperature goes up to 10 million degrees. So there is this theory, but theory is going to be corroborated and by the specific observations and by the result or the XRISM. And that's the process, and then the scientific mission is going to be made as for XRISM. Thank you very much for your talk. Next, Slim.
I would like to introduce Slim to you, and we have a video message from the project manager. So please take a look together with the video introduction of the project. Hello to everyone watching this live streaming event. I am Shinichiro Sakai, project manager of SLIM, Small Lander for Investigating Moon. I think you're all watching the live streaming with much excitement, waiting for the launch of SLIM. I feel the same. It has been 7 years since the start of the project. If you go back to when the idea was originally conceived, it has been more than 20 years. With the support of many and efforts of all those involved, we are now welcoming the day of the launch. We have dedicated so much efforts and great deal of thinking in SLIM, with which we aim to achieve lunar landing with unprecedented precision, to open the door to the next generation of lunar exploration. We are determined to stay focused even after the launch. From the era of landing where we can to landing where we want. Please continue to support us. From Professor Sakai, project manager, we have heard a very strong message. And we have Professor Mori, who is a member of SLIM project, and Professor Otake, payload manager. We are still watching the launch sequence, but how do you feel? Project manager, Dr. Sakai, said that from the era of landing where we can to landing where we want. That comment was mentioned. I think this is a symbolic phrase of the landing by the SLIM. Lunar exploration in the future will lead to leading-edge observation, and for long-term sustained observation, precise pinpoint landing is essential. And SLIM will be taking on the challenge of precise pinpoint landing to open a new era. Thank you. Pinpoint landing was mentioned, and we will come back to this point later for more detail from Professor Mori. But Professor Otake, would you like to comment? Yes. Watching Sakai-san's video once again, and watching after the SLIM video, I'm also feeling the renewal of my determination, and I also feel a great deal of excitement. And as Professor Mori mentioned, pinpoint landing from scientific viewpoint is very important. Where in the moon, what geology exists. To an extent, we understand that, and we therefore have a place in mind where we would like to conduct research, and in a targeted location to achieve landing is very important. Researchers are hoping to land on some precise point, and that is known because of the past missions. You know the distribution of substance in certain areas. So in the next mission, there is a more precise targeted location for landing that is being aimed at by this project. So we would like to ask more about that later.
Now, there are some questions about SLIM. We have received them. On the back, you can see the mock model. Let us use this model to ask questions. The one thing I would like to ask of you is that this body on the left-hand side, this triangle, cone-shaped silver dent, what is it? This is antenna, S-band antenna. There are several of them, as a matter of fact. And so at whatever directions, the vehicle will be able to be engaged in communication, and thrusters as well, which are attached. And I will come back to this point later on. So on the back, on the right-hand side, so the small-sized components are gas thrusters. The brown one is the main engine, and smaller ones are 22 Newton small-sized thrusters. So they are going to be combined together for landing operation. Thank you very much. And that is the answer. This is the S-band antenna for telecommunication. Thank you very much.
We have another question. Maybe I should ask this of Professor Otake. Do you yourself would like to land on the moon? And if so, what would you like to do on the moon? Yes, I would very much like to visit moon. That is the place that I would like to visit the most. And if I'm on the moon, because I study rocks, as I mentioned earlier, I would like to bring back rocks to analyze further. There are many rocks I would like to bring back. So I would like to collect rocks more than I can carry and analyze them as much as possible. Moon scientist would like to go to the moon, but as a solar scientist, if I visit the sun, I will be burned. It's difficult to visit the sun.
I think the separation of a SLIM is going to take place soon. So we will switch the camera to Tanegashima Space Station.
Tanegashima 宇宙センター竹崎総合司令塔から H-IIA ロケット47号機の打ち上げ実況放送を再開します。
This is a live coverage of the H-IIA launch vehicle number 47 from Takesaki Launch Control Center at JAXA Tanegashima Space Center.
ロケットの追尾は再開されており、現在ロケットは完成飛行を続けています。
We have restarted tracking the H-IIA. The launch vehicle is currently in a coastal state.
下部衛星フェアリングが分離していることを確認しました。
We confirmed that the lower payload fairing has been jettisoned.
第2段エンジン第2回燃焼開始。
The second stage engine ignition for the second time.
第2段エンジン第2回燃焼停止。
The second stage engine cut off for the second time. Separation.
SRIM の軌道への投入を確認しました。
SRIM has been inserted into the orbit.
これをもちまして H-IIA ロケット47号機によるXRISMおよびSRIMの打ち上げ実況放送を終了いたします。
We will now conclude our live coverage of the H-IIA launch vehicle number 47 with on board XRISM and SRIM.